Let's go.
Okay, we ready?
We are.
Okay. All right. Oh, sorry for the short delay, everyone, but welcome back to the Astro Imaging channel. We have a special presentation tonight from Dr. Brian Kloppenborg from the American Association of Variable Star Observers, and he's going to talk about how we can contribute to the scientific knowledge on these variable stars. And I'm particularly interested in this because I've also been part of other scientific studies where people need scientists, real scientists need data for some project or another. And we have a really huge advantage over professional observers in that we have telescopes and we have telescope time, that we can allocate that telescope time to whatever needs to be done. Whereas professional astronomers and big telescopes, that's very difficult to get time and space on that. So Brian's going to talk about the variable star program and how you can contribute to it. And I will turn it over to him in just a minute. I just want to briefly go over the calendar. We don't have to show it. We have Brian tonight. We don't have a show next week. Obviously, it's kind of Christmas time. But we have one on January 4th after the new year by Manny Lentz, who is going to talk about exoplanets, and then skip a week. And then on the 18th, Warren Keller is going to be back. We haven't had Warren for a while. And on February 1st, Mike Cranfield. And if you don't know Mike Cranfield, he has done lots of very clever things for PixInsight. And after the February 1st show, we have a lot of open dates. So as usual, we encourage anyone that has an idea for a program or processing or something to do with astrophotography, drop us a note, go to the astroimagingchannel.org, go into the contact page and just say, hey, I got something to talk about. One of us will get back to you and we can schedule you on the show. We like to have presenters, we like to have points of view, which perhaps are a little different than what we've done in the past. So please, if you have an idea, let us know about that. Now I'm going to turn this over to Brian and talk about AAVSO. Brian,
right.
show is yours.
Yeah, thanks for the introduction, Eric. So I'll go ahead and share my screen here and get the presentation up and running. So you should be able to see my screen now, right, Eric?
Once again, I've muted myself, so it takes us now you know what the delay is about. Eric, are you there? Yes, we're here.
Okay,
yes,
all right.
Your screen.
Yeah,
thank you.
And by the way, I will be calling on you guys, so make sure you keep your finger near that mute button, right? So that we're going to try to stump the hosts a couple of times during today's program.
Oh,
so
that will be easy. That'll be easy.
Yeah. Oh no, you'll be fine. So, so thanks. Hello, everybody. I'm Dr. Brian Kloppenberg. I'm the executive director of the AAVSO, and tonight I'm going to talk about how you can become a scientific observer. Basically, just kind of your path to contributing to real astronomical research. And I'm going to go a little bit further beyond what Eric mentioned just a little bit ago. So, classically speaking, folks know the AAVSO for variable star astronomy, but it turns out that we actually have 4 different key science focus areas. That's what I'm going to talk with you about this evening. We have stellar photometry, stellar spectroscopy, exoplanet photometry, and sunspot counting. And with each one of these different areas, I'm going to tell you why these things are important and why you should be contributing to science in these different ways, what you need in order to get going in these different fields. And in some cases, you can get started just with your own eyeballs. And in other cases, you need fairly sophisticated equipment. And lastly, I'm going to show you a couple of examples from just maybe the last year or two where amateur astronomers, much like yourselves, have actually made a real impact to astronomical science. So let's go and get going. So as Eric was mentioning just a little bit ago, amateur astronomers have a real advantage in that, you have your own telescope in your backyard and you can do anything that you want with it. And professional astronomers have a really interesting problem where they really can't monitor everything that's up there in the sky. And so a couple of examples is my organization, the AAVSO, we know about there are about 10.2 million different variable stars up there in the sky, but we only have data on about 34,000 of them. Caltech has a sky survey program that they've been running for maybe about the last 10 to 15 years. It's called the Zwicky Transient Facility. Every single night, it produces about 10,000 alerts. And these are things that they as the ZTF researchers think that they should follow up on, but they only have resources to follow up on about 10 to 15 of them. And then as we move into the LSST and the Vera Rubin Observatory era, we're expecting that facility will generate something about 100,000 alerts every single night, but they really don't have the resources to follow up. And this is where amateur astronomers can really make a difference. And again, the 4 key areas where I'm going to speak with you about tonight are stellar photometry, exoplanet photometry, stellar spectroscopy, and sunspot counting. So first, let's talk about stellar photometry. So why does stellar photometry actually matter? After all, we at the AAVSO have been doing it for about 115 years. Well, fundamentally, what you're doing is you're monitoring the brightness of stars to reveal how they're changing over time. A lot of stars, they pulsate radially, so as different physics occurs, not necessarily within the core of the star, but at outer layers of the star. You can kind of think of it as a series of an onion layer moving out. Some of the opacity changes in terms of the star, and it causes the layer to swell. And then when the opacity decreases, then you could have that same layer shrink, and that causes the whole star to pulsate in and out. We also have stars that they pulsate in non-radial patterns. So you might have heard about astroseismology, for example. They're measuring very high order modes in the stars. And from this information, you can actually tell a lot about what is actually on the interior of the star. Beyond that, you can also see eruptions. So everybody, including myself, is waiting for T Corona Borealis to erupt. There's eclipses. One of my favorite stars eclipses once every 27 years. So I might get to see it maybe 3 times in my lifetime. And then there's a whole bunch of other different astrophysical phenomena that are out there. And if you wanted to get started in stellar photometry, what you would need is really, you could start off just with your eyes or a telescope or a pair of binoculars. Or if you have like a DSLR or a mirrorless camera that can save raw images, you could get going in that area as well. Or as the folks here within the Astro Imaging channel would have, a telescope with a mount and some kind of a digital camera behind it would actually be even better. So here's where I'm going to call on the hosts of this show. So we're going to do a quick little exercise here. So Eric, Jaime, Linda, and Alex, if you guys could come off mute for just a second. What we're going to do is we're going to try to estimate the magnitude of Betelgeuse in these diagrams that I'm going to be showing you. And here, Betelgeuse is the star that's noted by the little crosshairs here. And we're going to try to estimate its brightness relative to Rigel down here in the bottom, which is labeled 0.1 in terms of its magnitude. And it's actually 0.1, but we omit the dot in our star charts because that could be confused with a background star. And we're going to compare it, say, also with this 2.1 star down here in the lower left-hand corner. So Eric, I'm going to call on you first. So does, yep, I got to get you there, right? So
this is just like high school where
it is, right?
Raise your hand.
Well, I couldn't see your hand raising, so I just had to, call on you. So
No.
yeah, so first off, so in this first image, would you say that Betelgeuse is brighter or fainter than Rigel in the lower right-hand corner?
It looks very similar.
It's pretty similar. How about compared to the 2.1 star? Is Betelgeuse brighter or fainter than the 2.1 star?
Well, doesn't it depend on the distance from
Well,
Earth?
actually, so in these charts, the brightness is effectively a measurement of the size. So the bigger the star looks, the brighter it is in this type of an image. So if this is the 2.1 star down on the bottom, do you think Betelgeuse is brighter or fainter than the 2.1 star?
Brighter. I hate to answer because I think I'm wrong.
No, you're right. It's a little bit brighter. So we would say, where would you say? Do you think it's closer to 0.1 or 2.1 in terms of its magnitude?
Just from the size, it looks,
just from the size. Yeah.
it looks like about a 4.
Okay. So maybe 0.4 or something like that. Yeah.
Yeah,
Okay. That's fair. Yeah, that's a good estimate. So next up, let's see. So how about Jaime? Can I pick on you next?
Yeah, sure.
Okay. So all right. So same kind of exercise. Here's Betelgeuse in the upper left-hand corner. Is it brighter or fainter than the 0.1 star?
Given the size, it should be fainter in this
Fainter.
case.
Yep. Okay. How about compared to the 2.1 star?
Yeah, that's about the same, but it is still fainter.
Still a little bit fainter. So
Yeah.
if you were to say, if this is 0.1 and that's 2.1 magnitude, where would you put it on the magnitude scale?
So in this case, Betelgeuse would be 3.0 star or something between 2 and 3.
Yeah, yeah, that's a reasonable guess. Yep. All right. And so, Linda, I'm going to pick on you for this last one.
Oh, we're doing
Again, so Betelgeuse in the upper left-hand corner, brighter or fainter than the 0-1 star?
fainter,
Definitely fainter. Yep. Compared to the 2-1 star,
brighter.
just a little bit brighter. So where would you guess it would be?
I'm gonna put it at like 1.8.
1.8. Yep, that works perfect, right? So, well, congratulations, you three. You three all passed. And so, you know, I agree with your estimates. They're pretty good. And you just learned how to estimate the magnitudes of stars visually. That wasn't that hard, was it?
I'm sweating.
Oh, yeah, I was sweating too.
Okay. So, you know, just kind of as a fun fact. So, if you, you know, variable stars are everywhere. The bright stars that we see, basically every single bright star that you can see with your eyes is actually a variable star. Not all of them, but a vast majority of them. In the case of Betelgeuse, if you go back to like 2020, Betelgeuse was about 1.7 mag, which is kind of like the same brightness of like Bellatrix or Gamma Ori. But in 2022, it was plus 0.2 mag, almost as bright as Rigel. So pretty wide level of variability within the star. Now, since this is the Astro Imaging channel, I have to, you know, answer the question of, well, Brian, how do you do this, you know, digitally, right? And I'll just say that there's special software to do that. But the basic approach that you use to do variable star photometry digitally is almost the exact same thing that you do when you do your astro imaging. So you acquire a set of calibration images, just like you do your bias, you do your darks, and you do your flats. When you acquire your images, you try to make sure that your variable star that you're looking at is not saturated and has a signal to noise ratio of something about 100. And it's after you've used your telescope for a while, you can kind of get an idea of like how long an exposure that would be. And then use a technique called aperture photometry on the raw images. Now this can be either like a FITS image that comes off your astro imaging camera, or it can be like a raw image that comes off of like a DSLR, for example. And you can use Astro Image J, AIP for Win, or if you're an AAVSO member, we have some cloud-based photometry software called VPhot that you can use. Or you can also use JPL's tool called Exotic, which is more of an Exoplanet focus, but it works as well. And all of these software packages produce data in an output format that you can actually submit to the AAVSO. So it's really not too bad. Now, just one note, if you have a tricolor camera, you absolutely can contribute. There's a slight modification to how this process works. You need to actually debayer the images, and I would recommend using only the green channel. The blue channel and the red channel do also produce useful data, but it's really a little bit more tricky to calibrate those things compared to just the green channel data. So, you know, photometry from a digital camera works out pretty well. The one science area that I'd like to comment about is, you know, how many of you have heard of the great dimming of Betelgeuse, right? You might be wondering, how did we know about that? Well, it turns out that AVSO has an amateur astronomer. His name is Tom Calderwood, and he absolutely loves Betelgeuse, and he's been monitoring the star for a very, very long period of time. And he noticed kind of, so the down here in the lower left-hand corner, this is a light curve of Betelgeuse. Brightness is along the vertical axis and time is along the horizontal axis. And he knows how Betelgeuse normally behaves. It's normally somewhat sinusoidal, following this pattern that you see kind of in the dashed black line in the background here. But he noticed leading up to the end of 2019 that the star was fading, and it kept fading, and it got fainter and fainter. And so he got a hold of Edward Guinan at Villanova University, a colleague of his, and they said, hey, something weird's going on. And they published this in something called the Astronomical Telegram. And then they noticed that it kept getting fainter, and it kept getting fainter, and it kept getting fainter. And they published three more astronomical telegrams, just alerting the world that Betelgeuse was doing something interesting. And his work alerted the entire scientific community that they should go and take a look at Betelgeuse. And as a result of his work, Tom Calderwood, his name here is listed on this paper in the Astrophysical journal from not too long ago. And his data was actually used in this Nature paper that's featured here on the right-hand side. And these were images in the lower right-hand corner of what Betelgeuse looked like. And it's thought that it was a cloud of dust, basically, that Betelgeuse belched off. There's also some theories that there might have been like the binary companion that's been proposed to exist was partially shielding the system because of some dust or something like that. But largely, dust was basically getting in the way, blocking off about a third of the star or so. So now before I move on to stellar spectroscopy, are there any questions that came about the photometry stuff?
Um, the your yeah, there's a question from John at Astro. First off, John was very careful. Earlier in the presentation, you mentioned Betelgeuse 3 times,
Mhm.
and we have to be very careful with that because it can bring certain things if you say Betelgeuse 3 times in a row. Okay, so
Yes, yeah. Well, you know, there are Betel buddies too. So yeah.
okay. Are you going to use a mono camera with no filter, right?
So you can use a monochrome camera without filters, although that setup is really well suited to a type of variable star called cataclysmic variables. If you have filters in place, it turns out like a green filter in like if you have a monochrome camera with a green filter in front of it, that's very close to a V filter, a Johnson Cousins V filter, and so that's really useful there. So you know the idea is that um, these different filters that you put in front of a telescope, they tell us a little bit about the temperature and some of the physics conditions that actually are occurring in the star. And so it really is useful to use different photometric filters, whether they be red, green, blue photometric filters or like Johnson Cousins or Sloan filters. But you can also, of course, do work with a monochrome camera too.
So if we were going to, if you're going to sell us on this and we're going to
Mhm.
get out there and start doing a little bit of it, you'd say, hey, you know, use what you brung. If you got,
Absolutely.
you
Yeah.
know, okay. And then when we get a little bit more addicted, we're going to say, hey, we need a V filter or something like that, maybe.
Yeah, you know, my first venture into stellar photometry was actually with a run-of-the-mill DSLR camera. So just with red, green, blue, and I was doing I literally put a camera on a rock and was getting data. And so you know, you can get started as long as you can get access to the raw data from the camera. So no JPEGs, but raw images or FITS images. You can do stellar photometry with it.
Okay, great. Now, I want to remind people that you got that comment section over there. Just you type in your questions and we'll
Mhm.
get to various places in the presentation and we'll go ahead and ask Brian what we need to know.
Yeah, certainly.
Okay,
Okay, well,
thank you.
well,
We're good
yeah,
now.
certainly. Yeah, we'll kick into the stellar spectroscopy section. Oh, okay. So stellar spectroscopy, it's really important to astronomers because it allows you to study the chemical composition, temperature, and pressure conditions within stars. So you think about it, you're actually measuring the temperature and the pressure of a star that's, you know, thousands of light years away from Earth. It's really quite cool. And if you have two stars and they're orbiting around each other, you can actually see the Doppler shift of the stars as they move, so you can see their orbital motion. Now, to do this, you really do need to have a telescope, a mount. You have to have a spectrometer of some sort, and I'll show you a couple of different models of things that you can use, as well as, of course, a CCD or a CMOS camera. So this is unfortunately something that you have to do with digital detectors instead of being able to do something with your eyes, say like through a pair of binoculars. Now, in terms of the observing methodology, it's somewhat similar to what you would use for astroimaging. So you still take your series of calibration frames, you know, your bias, your darks, and your flats. But then when you go to get your scientific data, you have to do a bunch of things that are a little bit different. And so spectroscopy, this diagram that I have in the middle kind of explained what happens. So a lot of spectrometers, they have slits in the way. Some of them, like the Flex Spec 2 and the eShell 2 down here, they definitely have slits. The Star Analyzer 200, this is an 1.25 inch filter that'll fit right in your filter wheel, for example. It doesn't have a slit, but it's very similar to what you might see here. So basically, the starlight passes through a slit, and then it hits some form of a dispersive element. This could be a diffraction grating, it could be a prism, for example, and then it splits the light off into the representative, wavelengths that are there. And so if you have something like the Star Analyzer 200, this is actually what I have in my telescope here at home. I'll see a picture of the star, which would be basically just the straight starlight coming through, and then off to the side, I'll actually see its spectrum sitting off to the side up here. And when I go to take data with this, I actually focus, but you don't focus on the stars. You focus on the spectrum here, and that's one thing that often gets first-time spectroscopists. It often throws them up because they are used to focusing, with a standard algorithm on the star, but you really have to focus on the on the spectrum instead. You have to set your slit orientation. We won't discuss that in detail here. You have to take some wavelength calibration images. So you might have a special type of light that throws light into the spectrometer so that you can actually see where the different wavelengths are at within the system. And then really importantly, you need to observe a reference star, a science object, and then go back to a reference star after the fact. And then once you get done observing your science objects, go back and do wavelength calibration again, because the spectrometers and your telescope, they're all sensitive to temperature. And as things expand and contract within the system, the wavelength calibration of your instrument will change just a little bit. And then finally, at the end of the night, once you're done observing, you go and take some calibration frames on top of that. And so in terms of like impact, here's a great example of a binary star that was studied by both amateur astronomers and professional astronomers. I won't talk much about the data on the left-hand side, but I will talk about these plots that are up here on the right-hand side. This is actually a silicon line, a helium line, H-alpha, everybody loves H-alpha, and then an iron line that was observed by professional instruments and amateur instruments at the same time. In the case of like the silicon line, you can see this little black river that goes back and forth. This is actually a silicon absorption line. So there's less light being emitted in that particular area of the spectrum because it's being absorbed by silicon atoms. And you see it moving back and forth because this star in particular, from which this paper was, from which this data was taken out of, is actually a binary star. So you're seeing Doppler shift of the stars as they move back and forth from each other. And the thing I found really cool about this paper is the researcher was basically asking the question, can data from amateur telescopes be used for this particular scientific use case? And he came to what I think is a fairly cool conclusion. The answer is absolutely yes. He said that the data that was coming from amateur instruments was almost indistinguishable in terms of quality from that of a professional telescope that he was using. So, the science was very, very cool in this particular situation. And, they were able to not only see that the star was orbiting back and forth from each other, but also see, the H-alpha emission lines move from one side of the system to another side of the system as material was rotating around the system. So really cool physics that you can see with a spectrometer on the back of your telescope. Next, we'll go over to exoplanet photometry, and I think when we get done with this section, we'll go back and ask for some more questions, Eric. So exoplanet photometry is really kind of like the cutting edge science that's being done by folks on the ground. And if you imagine a star with a planet moving in front of it, and that star happens to pass in front of, the planet happens to pass in front of the star, it will dim the light coming from the star just by a little tiny amount. And it turns out that is actually detectable from the ground using, in a small telescope that you might have in your backyard, for example. And this matters to professional astronomers because it helps refine the timing of the orbits of these different exoplanets that are moving around the stars. And the reason why this really becomes highly important is that when you're a professional astronomer and say you're wanting to study exoplanet atmospheres, which you might have heard of them doing that, you have to know when that planet is going to transit in front of its host star. Because when you write a proposal for James Webb Space Telescope or Hubble Space Telescope, if you're going to ask for 15 minutes worth of time versus 3 hours versus a day worth of time, the more time you ask for, the less likely it is that you're actually going to get it. So it really helps in terms of scheduling time on big telescopes. And so to contribute to this, basically, if you have a monochrome camera or any kind of a cooled CCD or CMOS camera, you're basically ready to go. So you need a telescope, a mount, and some form of a cooled camera in this case. No filters are actually needed. So again, the technique of exoplanet transit photometry, if you have this star here in the background and you imagine this little planet is moving in front of it, and when it's not in front of the planet, the star will be brighter. And then when the planet moves in front of the star, it will dim a little bit. And as the planet transits across the face of the star, it'll stay relatively flat in terms of its brightness. And then when the exoplanet then leaves the disk of the star, it'll brighten back up again. And there's some dependency effects that are a little bit degenerate in this case. So this graph here is really just trying to show that if you have the same size planet but a smaller star, you'll get a deeper eclipse. Or if you have the same size star and a bigger planet, you will get a deeper eclipse. And so it takes a little bit of modeling to try to figure out what it would be. Now, I will say that exoplanet transits, they require a lot more planning and much more careful execution than stellar photometry, because you have to know precisely when that exoplanet is supposed to transit in front of the star. And spacecraft like TESS, for example, give us very good measurements of when that occurs, but to go back and follow up on it time and time again, you have to keep observing it. So in the lower right-hand corner here, I show some data from Tony Van Munster. He's with the Center for Backyard Astrophysics. And he showed this observation of just a small little exoplanet passing in front of its star, measured with a 350 millimeter telescope, and a now what would be relatively old, this is 2004 era, SBIG ST10 CCD camera. And you can see here that this eclipse depth, which is about maybe 22 millimagnitudes or something like that, it's relatively easily detectable with that type of an instrument. And modern CMOS cameras are actually much less noisy than older CMOS, older CCD technology, and so it makes it a lot easier to pick up on exoplanet transits when they occur. Now, in terms of impact, amateur astronomers are having a huge impact in this field. And so here's 3 different papers by 3 different groups that are doing exoplanet transit photometry. On the left-hand side, this is from a group called Exoplanet Watch. And if any of you have watched AAVSO's webinars before, you'll know Rob Zellum really well. He's the second author down here, actually a lot further down than second author, but he runs JPL's Exoplanet Watch program. In the middle here, this is a paper that's talking about so-called hot Jupiter, and they use data from the AAVSO's database. And then on the right-hand side, if you have a smart telescope, like a unistellar EV scope, for example, they actually have something that's built right into their telescopes that allow you to contribute to exoplanet science almost immediately. And so you can see just in the last couple of years, here's 3 different papers where folks like you have actually made a pretty big difference in terms of science. All right, so Eric, maybe I'll just ask again if you have any other questions that you'd like to relay before we go on to sunspot counting.
I don't know what we have online, but I have a question.
Yeah, sure.
So I'm assuming that the orientation of planets around suns in our galaxy is random, right?
Yep,
So
that's a reasonable assumption. Yeah.
So the only time we're going to see transits is when the orientation is we're looking at the edge. So
Correct.
what percentage of the stars in the sky that we can see have that orientation? And what are the odds of that orientation being true?
Yeah, I don't know the math, but so I'm willing to think that somebody on the channel might be able to work it out. I do know that there's about 4,500 known exoplanet host stars out of the billion or so stars that are within the galaxy. So it's a relatively small fraction. But the important thing here is that we do have spacecraft that are out there looking specifically for it. So we had the Kepler Space Telescope, or Kepler was running for quite a while. We have TESS, which is up and running as well. And then the European Space Agency is going to be launching a spacecraft called Plato coming up next year, named after the famous philosopher. And then in addition to that, NASA's flagship mission in 2040 is specifically going to be looking at exoplanet host stars as well. So there may not be a lot of them that are out there, but it's an incredibly hot field. And there's a lot of people that are interested in observing in that area.
Alex, any
Yeah.
questions online?
No, we're good on the questions, but I did want to tell everybody that this is pretty interesting stuff. I know a few people who do it. And one of them presented at Nightfall this last October, I guess. And we've asked him, Manny Lines, to come present something about his exoplanet search. And he showed us some pretty cool stuff, the kind of the graphs that Brian's been showing us here. And he'll be back on January 4th to tell us about how he does it with his pretty simple equipment.
Yeah, well, that'll be
Okay.
wonderful. Yeah. Okay.
So I have a question, and maybe you're planning to get to this, and so
Yeah, sure.
but what some of these things you can do with relatively modest equipment, and some of them seems like you need a bigger telescope. Can you talk about what size equipment you need to do these various things?
Yeah, so in the case of something like Tress 1 here, this is observable. It was a 350 millimeter telescope, but this is actually with modern CMOS detectors. This is something that you could do with like maybe a 4 or a 5-inch telescope. So the more aperture you have, the faster you can take data, and also the smaller the error bars would be effectively on a graph like this. But it's definitely something that you can do with something that's about 4 inches in size. There are exoplanets that have transits that are on the order of like 80 millimagnitudes, and so you really have to pick the target star to match well with your observing equipment.
Okay, so something that's generally within the reach, at least for some stuff, of the kind of equipment that we have.
Yeah, no, I've done it with a 5-inch telescope. I have an 8-inch telescope that's just right over my right shoulder here, and it's definitely doable with things like that. So you don't need half-meter size telescopes to contribute to this type of science. Eight inches is usually plenty.
When you're out trying to grab one of these things, how much of an evening is it? How long does a typical one that the amateurs find, how long is a transit?
It depends on the individual planets and their orbital configuration. Some transits can be relatively short, meaning like maybe 10 to 30 minutes. Other transits can actually last 8 hours. There have been a few, actually, I think this, I don't know if it was this paper from Unistellar or if it was another one, but they had one of the longest observed exoplanet transits, and they used unistellar telescopes all around the world to create a basically 24-hour continuous light curve on this particular star. So some of them can be quite long. To find these things, you can use something called the Swarthmore Transit Finder. It's hosted by the Swarthmore Observatory, and from there you can specify, the limiting magnitudes in terms of the total brightness of the system. You can also pick the duration. You can pick the depth of the eclipse. So you can go out and like use, once you get an idea of what your equipment can observe, you can really narrow down the types of transits that you'll be searching for.
Thank you.
Yeah, certainly.
I think that what you want to do is observe for your own pleasure, which is like our imaging, or observe to contribute to the scientific knowledge.
Yeah. Yeah, no, it's there's lots of people that go out there and they just like chasing exoplanets. Actually, I've been talking really about going out and observing with your own equipment, and that's what you would do with Unistellar or with the AAVSO. Exoplanet Watch actually has a couple of robotic telescopes that are out there continually acquiring data on exoplanets, and what you do is actually help them reduce their data. And so if you don't have a telescope, you can actually contribute, and they handle all of the scheduling and observing, and you just have to go through and reduce the data. And I think everything they have is out on it's like on a Google Colab or something like that, so you can actually run the code out on the cloud, so you don't even have to download software onto your own computer to make it happen. So okay, well, I will go ahead and go on to the last section of the program here, which is talking about sunspot counting. And just to warn you all again, I'm going to ask you to participate again in this part of the program. Sunspot counting. So why is it important? And for those of you that have been, enjoying the auroras that we've had here recently, maybe about like a month ago, we had beautiful auroras where I live here in Colorado Springs. And of course, that's due to solar activity. And, sunspots are correlated with solar activity. So if you've heard of the Carrington event, right, back in 1989, there were auroras seen as far south as south central New Mexico. And there's, reports of telegraph pylons up in Canada throwing sparks because there was so much ground current that was moving because of the changes in the magnetic fields. Back in March 10th of 1989, there was another large event, and there were auroras seen as far south as South Florida, and there were actually power blackouts in Quebec as well. And knowing when there are sunspots and knowing how they're changing over time is actually really important. And I didn't understand this when I first took this job at the AAVSO, but amateur sunspot data actually serves as not only the historical record for what has happened in the past, going clear back to the 1700s. But every new telescope that's being launched up into space, so every space telescope that's observing the sun, when they measure and count sunspots, using whatever algorithms they've developed to process their images, they actually calibrate it back to current ground-based observations coming from amateur astronomers. So not only do amateurs serve as basically the historic record keeper in this case, but we're also the ones that are helping calibrate all modern instruments that are up there in space. And so I think that's just a really cool thing to be able to do. And so if you want to contribute to doing sunspot counting, you can either use something that's a projection setup, and I'll show you an example of what that looks like here in a moment, or you can use a telescope or binoculars with appropriate solar filters in place. And naturally, that brings me to a disclaimer, right? The sun is extremely powerful, and observing it without the appropriate equipment can be very hazardous. So, looking at the sun without a solar glasses that are checked every single time, you can have eye damage if you look at the sun and don't have the appropriate filters in place, or you can actually permanently damage your sensors in your cameras if you just get a little glint of sunlight. A couple of colleagues of mine, they actually had a 1 meter telescope that they left the dome open, and a little bit of light hit the mirror, and it actually started to burn some of the metal truss structures to hold up the secondary. And so, you do get a lot of power from the sun. So make sure that if you're going to go out and observe the sun, make sure that you have appropriate equipment in order to do that. Make sure that you read the manufacturer's instructions for how to observe the sun. And please make sure you check your equipment every single time before observing. If you have like a scratch on your solar glasses, or there's a crack in your solar filter, throw it away and don't try to use it, because your safety is incredibly paramount, and I don't want you to get hurt by looking at the sun. So with that said, if you go and observe the sun at optical wavelengths, basically the way that you set it up is you take your telescope or your eyes in this case, and you install your filters or your projection setup. Down here is an example of a projection setup kind of equipment where it's sunlight comes in here, bounces off a couple of mirrors, and gets projected onto some paper. Up above here, this is an example of a Takahashi telescope with a solar filter placed in front of it. And you point the equipment at the sun. People often ask, like, hey, Brian, if I'm not supposed to be looking through the telescope, how am I supposed to see the sun? And the classic answer is look at the shadows and try to minimize the total surface area of the shadow that's down on the ground. Works out quite well. And when you look at the sun, what you want to do is you want to record the date and time, the seeing conditions, the number of groups that you see, and the number of sunspots that you see. And we'll actually do an exercise here on the next slide. And when you're ready to report your data, the AAVSO has a program called SunEntry, which is a Java application. We're going to be releasing a web app here in early January that'll make it a lot easier to be able to report it. But then you can send your data into the AAVSO. So let's talk about how you actually count sunspots and groups. So a sunspot, as you may know, is a cooler region on the sun that's being caused by magnetic fields. Basically, it suppresses convection, so the area doesn't get as hot because you don't have upwelling of warm plasmas from the middle of the sun. And when we say a group is a collection of sunspots that belong to the same outcropping of magnetic flux. Basically, if you're looking here on the left-hand side, this big old blob here on the left, that would be a group. Each one of these sunspots then also is a group. Maybe this two here on the right-hand side could be considered just one group if you wanted to. All you do is you count the number of groups and spots. And seeing actually makes a pretty big difference here. You can see this big sunspot group here. It looks like it's just one big sunspot, but under better seeing conditions, you can actually split them off into maybe multiple spots that you can actually see within that diagram. All right, so an exercise for the viewers here. How many groups of sunspots do we see in this image? So Alex, I don't think I've picked on you yet. How many groups of sunspots do you see in this image on the left here?
I see 2 groups, I think, and 1, 2. No, I see 3 groups and a couple of 3 isolated. sunspots.
Okay, yeah, no, that's a good first round. In this case, I would actually say there's about one. This is a group up here in the north, and then in the south, here's
Group?
another group. Yep, here's another group, another one, and down here is another one. So I'd guess there's
Okay.
1, 2, 3, 4, 5 that are in this area. Yeah.
Then how do you distinguish between? I mean, it certainly looks like there's only one sunspot. Oh, you know what? Let me make that bigger. I have several things here that I have to look at during these shows.
Yeah, I know. I'm being mean because I'm
And
picking on you
yeah,
because you're
and
monitoring YouTube.
I
Yeah.
I can only see one sunspot in the ones over on the right.
Oh,
So
interesting. Okay.
yeah,
So maybe it's not coming through very clearly, but
yeah, maybe
okay.
that's
Yeah.
right. You know,
Yeah.
I just did an exercise for the Astronomical League
Mhm.
where I had to follow the sun for 2 solar cycles, basically 2 Earth months,
Yeah.
and count the number of sunspots and the number of groups, and give them their numbers and everything else, and report that for a 2 week period. But you had to get at least 20 some
Mm.
days worth of observation, and so I've had some practice on this, but I never was confident that I had the numbers right.
Yeah, and
You
actually,
know,
yeah, that's a really good point, right? Because you could imagine if you were to blur this out in a bad scene condition, like this little group down here at the bottom, near the sun's southern pole, you may not even be able to see that. And there's actually a really interesting way that we calibrate the different observers against each other. And so with the AVSO, at least, it takes a year. So you have to have a year worth of data that you've recorded before your data become effectively public to the rest of the world, because we have to calculate the so-called K factor
do
to
you give
calibrate it
people
out.
do you give people feedback on how well they're counting? So I never
I,
had any feedback on how well I was counting. I was just counting them,
yeah,
but nobody
yeah,
said, no, 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 you're goofing up. This is like you just
mhm,
did. No, that's a group. Okay, well, if that's a group, then I'm not counting right. That
yeah,
one,
yeah,
those two out there on the right, I count
yeah.
them as individual spots.
Oh yeah, so like this is a yeah, so a spot counts as its own group. So that this spot here
A
is its
single
own group.
spot can count as its own group.
Yep, counts as its own group. Yep, because it's
I
a
didn't see
grouping
that.
of flux. Yeah, yeah.
Didn't see that in any of the literature, and believe me, I went through a lot of literature for that practice.
Oh,
That
oh,
was the Astronomical League Sunspotter program.
oh man, I'll have
Brian,
to talk with them. Yeah, go ahead.
isn't all this published in the SDO?
So there's a couple of different places where things get published. Yeah, yeah. So the SDO is one of them. I also like the folks that they have a software called Lizard. It's a group up in Boulder that they publish all of it there as well. Yeah.
Now, what I mean is every day you can go to Sunspot
Ah,
regions, which is
yep.
data from the SDO, and they label and number
Oh,
each
yep.
one of these
Yeah.
groups.
Yeah,
In
kind
fact,
of like here on the right. Yeah, exactly. Yeah, so the thing is that they the images that are coming from spacecraft, for example, right? They're using algorithms to label all of those images, and then on the ground, people are also labeling them as well. But the ground-based observations serve as ground truth to these higher level algorithms, and so that's how they calibrate them all back and forth. So
yeah,
like here on the right hand side, and I'm sorry the image is not a very good quality, but you can see
yeah,
they've
that
labeled the
looks like
groups
from
here.
the
Yeah.
SDO.
Yep.
The
Yep.
reason I know
Exactly.
this is that we have a solar telescope, a narrowband,
Hmm.
an H alpha solar telescope, and every day when I'm imaging, I go directly to the SDO
Hmm.
output to see where we're going to image.
Yeah. Yeah. Nope.
And just to clarify, there are 5 groups, and there are 5 groups of those with the labels.
Yep. There are 5 with the labels there. Yep. Yep.
Okay.
That's right. All right.
That's
So
Keep Looking Up was asking that.
So
okay. Yep.
my question is, so the ground-based observer is a check for things like the SDO data?
Yeah, it's actually I think on my next slide I've got an example of how this works. And so there's really two large groups of people that collect data on sunspots. On the left-hand side, this is the Royal Observatory of Belgium. It's often referred to as like the Belgian sunspot count. And the right-hand side, this is the AAVSO's data. The Belgian group goes clear back to 1700. The AAVSO didn't actually start collecting data until 1945. But if you think about like when the first satellites were launched in the 50s, there hasn't been a whole lot of cycles, solar cycles, where we've had ground-based observations and we've also had space-based observations at the same time. And so that's why you really have to have continuous ground-based observations as well, because you need to be able to connect what we're seeing up here in 2025, with these automated algorithms that are, counting sunspots and groups from satellite data, and tie it back in with what we were observing on the ground back in the 1700s. And so, we've only, so 1950, so 1951, is that when Sputnik launched? 1955, somewhere in there.
58.
58.
57, I think.
Oh, no, it
50,
was before.
57?
57. Okay. So
57, yeah.
Right in here, right, we've had 1, 2, 3, 4, 5, 6, 7, solar maxes since then. And that's not really enough data to go back and use all of the data that we've seen here in the past. So it really is important to have ground-based observations to continue, to provide a good degree of overlap between what we're seeing in space with machines detecting sunspots versus what we've seen on the ground, especially if you want to compare it back to stuff in the late 1800s, like our Carrington event friend I mentioned just a few minutes ago. All right, so now here's the question: is like how
Could we
oh, go ahead.
hold up for a second or three?
Yeah, sure. Yeah.
We had some questions that we didn't cover at the time. Keep Looking Up has asked a few of them. And you spoke of a spectrograph on the back of a scope to capture the dips in the light. Aren't those spectrographs kind of expensive? Well, the question is, how can you do that with a non-expensive scale?
Okay.
So,
Yeah. So I'll pull up I'll go back several slides here. So sorry about the blinking here. This is an example of a couple of different spectrographs that are available nowadays. So this Star Analyzer 200, this is really a useful tool for you if you're just getting started in spectroscopy and you want to learn the entire process and study, look at different types of stars. It delivers a resolution of about 200, or an R of about 200. If it's properly configured, you can actually get it up to about 800 or so. And these are really good for exploring, just basically getting used to spectroscopy and exploring the universe. They're also incredibly useful for following nova, because they let a lot more light through, and so you can follow a nova as it fades, or a supernova as it fades for a longer period of time. These things, I think you can get them for about $200. So they're kind of the price of a standard astronomical, like a glass filter for science, basically. So not terribly expensive. This middle device here, this is a FlexSpec, and they have a FlexSpec 2, I think they've come out with now. These things are a DIY kit. There's no commercial company that makes them yet. And the spectrograph itself, I think, is around $1,000 in terms of buying all the parts. And then, of course, you have to put it together. And put it together also involves like wiring as well. So, those of you that are technically inclined, you could build something like this. This thing delivers a resolution of about 1,000 to 1,500. At that resolution, you can actually start to do stellar spectral classification. And for some of the more rapidly moving binary stars, you can also see the motion of some of those binary stars. But there's probably 1,000, I would guess, or so stars that you could measure at that resolution that are binaries. And so you also have to put a astronomical camera on the back of this. So like a QHY or a ZWO camera on the back of this, maybe $1,000 to $2,000 on the back of this as well. Down here, this is a product from Sheliak called the eShell spectrograph. And unfortunately, I don't know the price, but it's more expensive than what the FlexSpec is, probably by at least a factor of 2, if not 3. But the interesting thing here is that this device allows you to get very high spectral resolution across the entire spectrum. And whereas the flex spec gives you medium resolution across the entire spectrum, and the star analyzer is low resolution over the whole spectrum. So if you wanted to get started, I would say something like the Star Analyzer 200 would be a reasonable place to get going, just to learn. And then if you like it a lot, you could upgrade to something like the Flex Spec later on. The AVSO, by the way, I'll mention here in a little bit about our robotic telescopes. We actually have some robotic telescopes with star analyzers in them, and we're getting ready to deploy a telescope with a different type 3D printed, not a flex spec, but a different type of spectrograph on the back of it as well. So for an AVSO membership, you could end up getting access to a spectrograph as well.
Okay, there's a third question down here that
Yeah.
about when you find an exoplanet,
Mhm.
do you report it to TNS or whereabouts? How do you report it? But I think there's another question that I've got to ask in,
Mhm.
in seeing how this is phrased. Are you suggesting that we go out looking for looking for exoplanets, or just looking for, the ones that have already been discovered, and we trace them to verify it and stuff like that? What are you asking us to do?
I think it's a much more productive use of your time to follow up on stars that have known exoplanets and ensure that the orbital information we know about the exoplanets is really quite well known. The reason for that is there are several space-based survey telescopes. TESS is the most popular one that's being used right now, that will sit and monitor a particular very large field of the sky for something like a month. And during that time, if there's transits, it's very, very sensitive. So um, uh, most of the ground-based telescopes, you can get to maybe like 5 to 10 millimagnitudes of accuracy. TESS can get to 0.1 or better millimagnitudes of accuracy. So it's much more sensitive. And the nice thing is they generate preliminary orbits for you so that you have a better chance of actually observing a transit. So I would
Okay.
say the follow-up is probably the best thing to do. Yeah.
So we're not after so much initial discovery as following up and verifying and getting duplicate data. Now,
Mhm.
having done that, what do I do with the information?
Yeah. So you can submit it to a variety of different places, and I'll pull up that slide here again here. If you can submit your data through Exoplanet Watch, it ends up coming into the AVSO's database, or you can submit it to the AVSO's database. We have an exoplanet database specifically to accept that type of data. Now it has to be reduced, right? So it's not just raw images. You have to do some processing on it. But once it comes into the AVSO's database, NASA JPL actually ingests that data on a daily basis to update their estimates of the orbital parameters of different exoplanet stars. So it's continuously feeding back in and making our knowledge of exoplanets better.
Okay, thank you. And that catches us up.
Mhm.
Looking up, keep looking up here. Notice that when she saw her Nova and M31 on October 25, she never quite got it reported up to TNS because she couldn't sign on and stuff like that. But
Oh, okay. Yeah.
there's ways to learn that, I guess. So
Yeah.
okay,
Yeah. Yeah. There
uh,
definitely is a learning curve. That's for sure.
that is all the questions we got on the
Okay.
chat right now.
All right. Well, so speaking of the learning curve, I will say that, as a person that got a PhD in physics with an astrophysics specialization, I will say science is never easy, but it's actually really rewarding. And just to let everybody know, right? Science is actually incredibly real work. There definitely is a learning curve. The data that you get is going to be messy. Your instruments aren't going to always work correctly. So, Alex, I think you were mentioning like your focuser is on the fritz right now. And clouds always seem to roll in at just the moment when you're trying to get the data that you need. But for groups like the AVSO, we're here to help you, and you really don't need to know everything to get going. So I think that I learn best by doing, and I'm not even going to claim that I'm an expert on any of these specific things, and I make a lot of mistakes. I actually between me and my staff astronomer Bert Pablo, We grade all of the spectra that come into the AVSpec database to look for common issues that occur, and then also give our users feedback all the time. And just on Friday, somebody submitted a spectrum of a star that was Doppler shifted by about 325 kilometers per second. And I asked him to go check his wavelength calibration, and he said, no, Brian, this is real. You should have accepted the spectrum, and that's the way it went. And I went ahead and accepted it. So the important thing is that we as a group are willing to help you out, and we're willing to work with you as you're going through the learning process. And on the right hand side, here's an example of our last annual meeting, or no, 2 annual meetings ago that we held down in Huntsville, Alabama. So if you're interested in about any of the topics that I've discussed tonight, I'd suggest that you go and check out the AAVSO's website and look at our observing manuals. These are free resources from the AAVSO. We have manuals that cover visual observing of variable stars, how to use your CCD or CMOS camera, how to conduct stellar photometry, or even your DSLR camera to do stellar photometry. We have a solar observing guide, which will walk you through how to count sunspots, and how to count groups, and how to count sunspots, and the different ways that you set up your equipment to make sure that you do it safely. A good colleague of ours, Dennis Conti, has written a practical guide for exoplanet observing, and then we even have a manual for how to get started in spectroscopy. Now, these do tend to be somewhat long. They can be a couple hundred pages, but they are very detailed. And if you like to learn via YouTube, you can also check out the AVSO's YouTube channel as well, where we have bits and pieces of these manuals that we've discussed over the years. And speaking of that, we also have a variety of webinars. So far we have over 200 videos covering all of the different topics that I've discussed, as well as data analysis and programming, things like that. So if you're curious, check us out over at AAVSO HQ on YouTube. And you heard me mention a few moments ago that if you don't own a telescope, we have telescopes that are available. Here's an example of what we have. So if you're a member of the AAVSO, that means that you've purchased a membership within the organization. A full membership is $105 a year. That gets you access to 8 different robotic telescopes that are around the world. We have 5 of them that are configured specifically to look at bright stars, and these are Takahashi E180s, so very, very good quality optics. And then we also have 3 faint star monitors, actually 4 now, because we just brought another telescope online about a month ago, and they have 20 to 24-inch apertures, so really large. These instruments are designed to do science, so they're not made for doing astrophotography. So they're equipped with Johnson Cousins, Sloan, and H-alpha filters. We have some spectrographs that are available. I say coming soon here, but they're already in the filter wheels. It's just that we haven't turned them on. Now, AVSO operates its telescope network much like a telescope allocation committee would be doing at a professional observatory. And that means that you have to submit a proposal for what you want to do and how you want to do it. But I will say that we're very friendly people. We had a young lady in high school. She asked to observe NASA's DART mission, and she said she wanted to see what happened when the impactor hit the surface of DART. That was her entire proposal, and we said that sounds interesting. Let's do it. We're a really good group of people to work with, and so if you become a member, you get access to these facilities. You could go out and do stellar photometry or stellar spectroscopy. And if you have a robotic telescope of your own that you're interested, like you're not fully utilizing the observing time there, feel free to reach out to us, and we can see if we can get it integrated into our network, for example. So I would say, if any of this is interesting to you, get out there and start doing some kind of variable star science. So the AVSO can help you learn more about stellar photometry, stellar spectroscopy, exoplanet photometry, or even sunspot accounting, and you can start contributing to something that's been going on for over 115 years. And so with that, Eric, I'll go ahead and stop sharing my screen, and we'll answer any questions that exist.
Okay, I'm back. Yeah,
Well,
that
good.
was great. We've had a couple of presentations on this before, but there's always something new to learn. And thank you. I've learned a few things by listening to it. And great presentation. You held your audience. In fact, your audience got bigger over time. I'm not sure how that happened, but A friend probably called a friend.
Yeah, maybe.
Alex, do we have any more questions that popped up in the last 5-10 minutes?
No, we're good on questions right now. Everybody's
on
been
questions.
asked.
By the way, we kind of hang on after we end the show, and if you'd like to stay for a little bit, you're certainly welcome to.
Oh, certainly. This has been a lot of fun.
Yeah.
Brian, as someone as you've worked with people and seen what the learning curves that people go through, how long do you think it takes most people to actually start being productive at one of these endeavors?
Yeah, that's a wonderful question, Linda. I would say it's highly dependent upon the individual, right? And how quickly you pick up on different tools. So I've had a couple of young high school students that worked with their teacher, and they were producing useful data within 2 classes. I've had some other folks that took a lot longer than that. So it just really depends on how much you want to get into it.
So the
And
variabilities in the person.
yeah, there's
more
some variability there, but one of the if you want to give this a shot, there and let's say you just have your normal astrophotography rig, right? And let's just say that you have like a monochrome sensor or something like that, right? There are a class of stars called high amplitude delta Scutis that pulsate back and forth by about 0.8, 0.9 magnitudes, and they do it in about 120 minutes. And so these are really cool because you can go out to a star party, and like within one star party, you can get a full light curve of a star. And it's just phenomenal to think that something that's as big as a star can pulsate back and forth, within 120 to like 180 minutes. So if you'd like to know more about those, I think I've got a blog post about them on the website. We're getting ready to launch a new website in early January, and I absolutely know that content's there. So we have recommended targets for people to go and observe if they're really interested in getting going.
And these are pulsating stars, not 2 stars rotating around each other, or
No,
planets.
just a single star that's pulsating inwards and outwards, 120 minutes to go out and back in.
Cool. Well, I think we're all set. Who's running the program? Jaime, are you running?
Yep. The streaming. Yep.
Yep. I think we're all set. So thanks again, Brian, for being here, and thanks everyone for listening. And we'll see you, I guess, after the new year, right? That's next presentation.
Yeah, which
Oh.
incidentally is about
Exoplanets.
transits.
Exoplanets.
So you'll see how some of this works.
So
Sure.
for everyone out there, have a happy holiday and a happy new year, and we'll see you in January. So good night, everyone.
Happy
Adios,
holidays. Have a good night.
Happy Christmas. Happy Hanukkah.
Happy solstice.
Yeah.
Yeah, that's today.
Yeah, it is.
Shortest day of the year. It's too bad it's
Yeah.
cloudy at our observatory.
Nope. It's just going to get brighter from here on out.
Yeah, it's actually clear here tonight, but I didn't even try to set up with this cold.
Yeah. I haven't gotten my gear out for the last couple of nights. It's been really windy. I live in Colorado along the Front Range, and there's been really high winds the last couple of nights. So I observe from my I live in a condo with a covered patio that faces north. And so, people are like, "Hey, Brian, what's the moon doing?" I'm like, "I don't even see the moon."
Well, you got the wind coming over the mountains that causes a bit of turbulence too, don't you?
Yeah. It can get.
You're on the east side of the mountains.
Yeah, it can get pretty bubbly. I have about my scene is like 2 to 3 arc seconds on most nights. Usually at like the 2.8 is where it averages. So, it's a little, it's not great, but I'll live with it.
Are you at Colorado State?
I'm in Colorado Springs.
Colorado. Where's Colorado State?
So is there
I'm
a
sorry.
Colorado? Yeah, there's CSU. There's a Colorado State University, Denver. They have a whole bunch of different campuses around the state, I think.
One of our grandsons is